Our last seminar this year. The seminar will be given by Professor Białynicki-Birula, and it will be about Dirac equation, actually, 90 years later. And also a small announcement after this talk, we will have coffee and cookies upstairs. So you are all invited. And it's sponsored, or it was done by Science and Coffee Seminar, which is our friendly seminar on Monday.
Indeed, Dirac equation is 90 years old, and the famous paper will be shown in a minute. This talk is based on my joint work with my wife, and this is, as you see, Dirac with Feynman in Jablonna. And this is the famous paper. Interesting remark, it was presented by Fowler in January, it was printed in February. So that was how editors worked in the good old days. Okay, what I want to tell you is that I think, no, presented. When it said presented by Fowler, that was like in bulletin of the Polish Academy of Sciences, the person who presented this took full responsibility. And Fowler was the person who presented most of the Dirac papers published in the Proceedings of the Royal Society. Okay, so by the way, I met Dirac several times. One meeting was memorable. That was in Jerusalem when there was a celebration of general theory of relativity. And then during the walk with Dirac, I asked him a very simple question. In those days, I was interested in nonlinear form of quantum mechanics, and I asked Dirac whether nonlinearity may play a role in quantum mechanics, and Dirac said no. And that was the end of this conversation. Well, Dirac equation is 90 years old, so one would think that there is nothing that has not yet been discovered. However, as time progresses, there are various connections which are new, and these connections, I think, may lead to something interesting, as I will try to show. So, what will be the new thing about Dirac? Hopf vibration. How many of you know what is Hopf vibration? Please don't hesitate, raise your hands. Not too many. Okay, not Heinz Hopf. Okay, so I am glad that most people don't know, so at least they will learn what is Hopf vibration here. So this is Heinz Hopf, who wrote his famous paper. My specialists in topology say that that was really a crucial paper, even though it was relatively simple. I will show some pages from this paper. Heinz Hopf was born in Grabiszyn, which is a suburb of Wrocław. He studied at the university there. And interesting thing about this paper is, will be seen in a moment, vibration. Let me just give the most trivial case of vibration. Vibration is a result of a map. If we map something from a bigger space to a smaller space, that means that many points in the bigger space will be mapped to one point in the smaller space. So the simplest vibration is when you project, say, three-dimensional pictures on the plane, and then these lines are fibers. And that's all you have to know about vibration at the moment to understand the rest. So this is the famous paper by Hopf, and what I really liked about this paper was that it's written in plain language, even though it's deep into topology, but I will show you that this is something that I don't find too often in modern mathematics. One tries to use sophisticated language, as you perhaps know, some of you. The whole theory of fiber bundles started with Hopf. He was in Zurich. Even though his father converted, he was treated in Germany as a Jew, of course, according to the... So he worked in Zurich. And this is the end of the paper. And what is interesting here is what is written here. Hein im Riesengebirge. What is Hein im Riesengebirge? This is now called Przesieka. So he wrote this famous paper in Przesieka, which was called Luftkurort Hein. So there are some Polish connections. It's also this is close to Jelenia Góra. Yeah? Przesieka is. So this is the mathematical form of this vibration. I will write it down in bigger font in a moment, so you don't have to watch this now. This is in bigger font. So what you see now is a mapping. On the left-hand side, you have 3 functions. On the right-hand side, you have 4 variables. Therefore, many points will be mapped into one point in this 3-dimensional sphere. And when you do simple calculation, you find that this equality is guaranteed by these formulas. I think mathematicians now would not bother with such examples which are very concrete, and they give really formulas that can be understood even by high school students. So this is the equality. What does it say? Whenever these points are on the surface of a sphere in 4 dimensions, 3-dimensional sphere, then they are also on the surface of a smaller sphere. And to show you now something, let me now show you a beautiful... of that type, sure, but of course, yeah, there are many formulas, but what is nice is that Heinz Hopf wrote a definite formula, and this definite formula is considered now to be the... you will see in a moment. I have a movie now. Exactly, but this is the Hopf vibration. How does it work? Look, these are the circles that become points, and these are the points on the surface of the sphere, which is 2-dimensional. And this beautiful movie shows you what are the circles that belong to various points here. And this is the dance of the circles. And somebody really, I of course took it from the internet, but it looks nice, you have to admit. It's a beautiful dance. Okay, now you see. The colors indicate which points here correspond to the circles. And this is really neat. Okay, so this beautiful movie now will come. So now let's get down to business. So now where is the Dirac equation, and what is new about the Dirac equation that is connected with Hopf vibration? So this was the paper, this is Hopf, this is the simplest vibration, this is the paper. And now we go to Maxwell theory, because for the first time, Hopf vibration was found in the solution of Maxwell equations. And that solution of Maxwell equation has interesting history. It was discovered first by Singh. He's Singh, not Singh, because he was Irish. So this is Singh. In 1956, he found a certain solution of Maxwell equation that was localized. He liked it so much that he thought that this could be a model of the electron. Of course, this was absolutely not true, but he believed that this is a very nice solution. Antonio Ragnada later discovered that this solution is directly connected to Hopf vibration. Now, what is the solution? This is the integral which tells you that this function here is a wave packet of plane waves, and the weight function is simple exponential. When you do this integral, that's a nice... Yes, plane waves with frequency omega and wave vector k. When you do the integral, which is a nice exercise, you find that this is a nice algebraic function. No, what do you mean you... come on, no. Yukawa has nothing to do with this. No, Yukawa has R in the denominator, which is therefore different. Okay, so now what happens next? How is this connected to Maxwell equations? Well, there is a nice way to generate solutions of Maxwell equation that was discovered by Whittaker. Whittaker, who was later famous for being the enemy of Einstein. He didn't like Einstein. He said that everything was done by Poincaré, and in his 2-volume, very nice, interesting book, he prefers to treat theory of relativity as being done by Poincaré. Okay, so what did Whittaker discover, and we made a lot of use from that, is that when you have a solution of the wave equation, one solution of wave equation, of D'Alembert equation, which is complex, and that is complex numbers are 1. Okay. So when you differentiate this solution, you get a certain complex function f, and here it's written after differentiation. It's easy task to differentiate. Then when you separate this into electric and magnetic parts, which are the real part of f and the imaginary part of f, you automatically get the solution of Maxwell equations, in free space, of course. So, what are the lines of the electric and magnetic field that are characteristic for this equation, for this solution? Well, what are the lines? You have to integrate the trajectories that follow the lines of electric and magnetic field. So let me now do this for you using, and you will see what these trajectories are like. Namely, I have here the notebook in Mathematica that will do the integration. Here is definition of f. So what I do, I ask Mathematica to remember this definition. Then I split this into real and imaginary parts. Nice. And now I take, for definiteness, the electric part, and I integrate these equations. And what do we get? Hopf vibration. Electric and magnetic fields follow the circles that are also found in Hopf vibration. And of course, the beauty of this is that there is some stability because these are topological properties. Circles are closed, they cannot break because equations are analytic. And this is the connection, and this was for the electric field. Let me do it again for the magnetic field. Here they are. These are circles of the magnetic field. So that much for the Maxwell equations. So let's go back now to my presentation. Control L. So we know what it is, and let me write something which is worth remembering, namely the Maxwell equations for the vector F, which is the combination of electric and magnetic field, are of course having this curl here. However, in quantum mechanical notation, this curl can be converted into the scalar product of momentum, which is the derivative, with the spin 1 matrices. And photons, of course, have spin 1. Therefore, it's no surprise that the Hamiltonian for the photon is the helicity, the projection of momentum on the spin direction. So now we are ready to go to the Dirac equation. And this is a way of writing the Dirac equation, which is easy to remember. Otherwise, you have to struggle with gamma matrices, whatever. And now you just know that helicity, the projection of momentum and spin, this time it's a different matrix, Pauli matrices here, instead of spin 1 matrices. And this is the set of two equations, which is identical with the Dirac equation, only in a somewhat not standard representation of these matrices, which Dirac called alpha, beta, and then it was converted into gammas. When you put these two equations for two-dimensional objects together, you get the Dirac equation. And this is easy to remember, and this is a very convenient way to treat the Dirac equation, because you can now do something that Whittaker did for the Maxwell field. Namely, given any solution of Klein-Gordon equation, scalar equation, you take any complex function, then you can find that there is a solution of the Dirac equation, which is derived by simple differentiation. Differentiation is much easier than integration because it can most of the time be performed. And this is what happens. So how does one generate the solution of Klein-Gordon from the solution of the Klein-Gordon equation? First, we take the first spinor here. This is the first phi. The second is chi. The first, you take just this solution and put it on top because it's a two-dimensional object, and then place 0 here. Well, then you define the second spinor in terms of phi. What you have to do is to differentiate. You differentiate with respect to time, you differentiate with respect to space coordinates, and then it's an easy task to check, because that's not yet complete, that the second Dirac equation holds. And usually one struggles with the Dirac equation because there are 4 equations, interconnected between themselves, and you have to check that all the equations are satisfied. This is an easy way that should be even taught to students of relativistic quantum mechanics.
Does it help me to solve the hydrogen problem?
No, because this is for free particles. For interacting particles, life is more difficult. but it helps a bit. Okay, so now what do I do now, together with my co-author? Well, we just generalize this function that was used to do the Hopfian, as now it is called. This is in analogy to skyrmion. Elementary particle physicists like skyrmion, and of course this is allowed to use the name. Then it's written with lower case, like fermion also, from the name. So we construct now the Dirac Hopfian. Well, I use the simplified units. And how does this work? Well, I take combination of plane waves for a particle with a mass. And then I take the exponential, and that's all. This is the same wave packet in terms of the distribution of momenta as the one for the Maxwell Hopfian. And this can be performed. This leads to the Macdonald function, which is one of the family of Bessel functions. And it is a very nice function because it drops off exponentially for large distances. Therefore, it is a solution now, according to what I said before, of the Dirac equation. So let's go down now and study the properties of this solution. Well, the derivatives of this are also solutions. So we can generalize this a bit and differentiate with respect to x and y. And in this way, we derive twisted Hopfians, which are eigenstates of angular momentum, total angular momentum, because there's orbital and there's spin part. And this is the solution of the Klein-Gordon equation, endowed with the angular momentum. And let's see what are the properties of these solutions. These are the lines of current. We don't have electric and magnetic field to study the properties, but we have the current built from this solution. So when you take L equals 0, you get this nice picture, integrating the lines of current the same way I have shown you how to do it for the electric and magnetic field. So here we have the solution for L equals 0, L equals 1. And this is another picture that shows you the similarity between the Maxwell solution and the Dirac solution. What are these lines? These are the lines of the current, but of course, if I would plot it in 3 dimensions, you would not see, you would see the arrows, and this is much better to plot only 2 components of the current, and I've chosen different components. This is the x and y component of the current, and in Mathematica there is nice command, streamlines. These follow the lines of the current, and this is what you see here from these 3 perspectives. And now let's compare it with the Maxwell Hopfian. Look, this is almost the same, and this is the pointing vector now, which is the
XY components on XY plane?
no, these are XY components on the Z0 plane.
On XY plane.
XY Z0, okay. Well, yes, the reason is if I took the complex conjugate of this F vector, I could reverse it, but the more standard way is to use E plus IB. No, but I think there is some difference between electricity and the Dirac equation. So no, but also this picture is not exactly the same. Look, these are circles whereas here they do not close into circles. So there are some slight differences anyway. But I think that this is quite convincing that I am allowed now to call this a Hopfion because the properties are really very, very similar. So, I think this quote from Wigner is in place here. What was in this paper that Wigner wrote many years ago? There is a story about two friends who were classmates in high school talking about their jobs. One of them became a statistician and was working on population trends. He showed a reprint of his former classmate. The reprint started as usual with the Gaussian distribution, and the statistician explained to his former classmate the meaning of the symbols for the actual population, for the average population, and so on. His classmate was a bit incredulous and was not quite sure whether the statistician was pulling his leg. "How can you know that?" was his query. "And what is the symbol here?" "Oh," said the statistician, "this is pi." "What is that?" "The ratio of the circumference of the circle to its diameter." "Well, now you are pushing your joke too far," said the classmate. "Surely the population has nothing to do with the circumference of the circle." And of course, this is mentioned by me because, again, we have the same unreasonable effectiveness. There is Hopf vibration. It has something to do with spheres. And then you find that the relativistic particles with spin know about this vibration because they really have solutions with this property. So mathematics is telling us very often what to do with physics, even if we don't know any deep, there is certainly no way to understand some deep connection between Hopf vibration and the electron. But still, mathematics is telling us that there's something in it, and it may be useful.
Can be also seen as SU2 divided by S1, yes? So,
Yes,
and
yes,
then
yes,
SU2 is directly connected to angular momentum. So there is some like vague connection at least.
Angular momentum, I wouldn't be so sure because I don't see this. Well, okay. Well, of course, when you bring in group theory, then there is a lot of connections at the level of group theoretic properties, and this may have something to do with group theoretical properties. Now, there are various...
I'm still puzzled a little bit because these fibers, they have certain properties, general mathematic properties, right?
Yes.
Depending, of course, how you define the vibration. That's true, but
Yes.
if you assume something about vibration, you get that. And so it is therefore reasonable that if you find in your calculation a line which has the same properties, like a streamline for current of Dirac equation, which has to be closed, and because current cannot disappear, and differentiable perhaps because you just assume that your solution has good differentiable properties, then there is only a question which vibration results in this fiber. Whether you can, but there must be one basically, because probably there must be one, because every fiber, every curve which could be a fiber is probably a fiber of a certain vibration. Right?
Yes, very absolutely. No, but these special solutions are the properties of the particles that obey the Dirac equation. This is a localized solution, of course. Yes.
Okay. Is there any chance that it can be of some importance?
In a moment.
Okay, my question is, in case of skyrmion, there is a topological charge, a kind of topological invariant which somehow defines the solution, is there any kind of topological charge in these?
Yes.
These?
Well, many people even call the magnetic quantum number topological charge of states with angular momentum. So in this sense, because angular momentum does play a role here, we have a topological charge because angular momentum is quantized. In this sense, of course, it is a topological charge, cannot be destroyed. Now, why this may be related to physics? Because in recent years, there was a lot of experiments, new experiments, where people learned how to produce beams of electrons with some interesting structure. Many years, this was done for light beams. There are various kinds of beams, Bessel beams, other beams, which are produced in an easy way now because you have a hologram, you send light through this hologram, and hologram gives a twist, and this is how these structured light beams are produced. Now people are trying to do similar things. They call it twisted electron beams, and this is something that comes out here in this simple. Yes, relativistic, of course. And therefore, this could be something that leads to structured electron beams, whether they are useful in electron microscopy, for example, in other cases, I don't know. But it is worth knowing that there are solutions of the Dirac equation that have these properties. Now, I was talking about Hopfion at rest, in the rest frame. However, since this is a relativistic theory, it's a trivial task to push it to any speed because everything is invariant under covariant under Lorentz transformation. So one can make, and of course what will be discovered immediately is the shrinking, the Lorentz contraction of these states, etc. That would be rather obvious. One does not even have to do this in terms of the wave functions. One can use the current, which is a simple 4-vector, and we know how to transform a 4-vector.
But it's in helicity representation, so there's no problem with Wigner rotation.
Still, there is a lot of unnecessary calculations because at the end you want to see something that can be observed. So therefore it's easier to do this transformation on the current than to do it for the... this is something that I wanted to tell you, and I do recommend everybody who would be interested in solving the Dirac equation to use this trick. Of course, as I mentioned, unfortunately this works for free wave packets. For interacting particles, it's not that simple. However, when you take, for example, the hydrogen atom, you may ask the question, how much of this is present in the ground state, say, of the hydrogen atom? And that can be calculated. There's quite a lot if you take the overlap between the Dirac wave function for the hydrogen in the S state and this function. There's a lot of overlap because this function falls off exponentially, and this is the property of solutions in the Coulomb field. So
The wave packet which moves like a coherent state, like in the quantum oscillator.
oh yes, I was even involved in the first investigation of this problem. One can make from various eigenstates of the Hamiltonian non-dispersive states which are held together. They don't disperse because of the properties of these orbits which have additional stability due to the Coriolis force.
I know, but What is the connection with what you are presenting here with the box?
Maybe, I don't know. So I think that is all I wanted to tell you. If somebody has some questions, I will be glad to answer.
Okay, questions, comments?
What happens if you formally add this solution to, let's say, a plane wave? Does it change its properties drastically?
You mean to take the superposition?
Yeah, the superposition. Does some kind of topological add certain topological properties conserved or not so much?
I have not done that, but I am afraid this would just spoil the
I see.
solution. Yeah.
The plane wave doesn't have a definite angular. The plane wave doesn't have definite angular momentum, right? A plane wave.
Plane wave does not have
The definite angular momentum, and what is important for this stage is that they do have.
Okay, anyone else?
What comes to mind is that the heavy vortex solutions with plane waves give this fork-like thing.
Yes. Aha. Yes. 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 This is what they.
Maybe there is something also in the interference of this solution.
Yeah, I have a question concerning.
Information about
Yeah, I have a question concerning the m equals 0 Dirac equation, massless case, and because when you look at massless fields of any spin, you have something which is called the Robinson congruence, which looks very similar to your fibers.
Yes. The Robinson congruences are closely related to the study of solutions of Maxwell equations in the context of these Hopfians. And there was quite a lot of work on that in the literature. When Ranyada discovered these topological properties, then various people tried to connect this with Robinson congruences, and there is this connection.
Okay, so if there are no other questions, let's thank Professor Białynicki once again. And you are all invited